secrets, no secrets.
Welcome guys to today's class. In today's video, we want to discuss one of the important topics in chemistry, chemical equilibrium, as you can see on the board. Yes, this is one of the important topics in chemistry, chemical equilibrium. We can put this topic in another way. We can say we want to discuss when can we say that a chemical reaction has reached or attained equilibrium. We can also say again, what are the conditions necessary for a particular chemical reaction to reach equilibrium? So we can be answering the question of when and what. When can we say that a chemical reaction has reached or attained to equilibrium? And what are the conditions? What happens? What can make a chemical reaction to reach equilibrium? Okay, let's answer. A chemical reaction can be said to reach or attain to equilibrium when the rate of forward reaction equals the rate of backward reaction. I repeat again. A chemical reaction can be said to attain or reach equilibrium when the rate of forward reaction is equal to rate of backward reaction. Let's write it. Rate of what? Forward reaction equals to rate of what? Backward reaction. That is about one condition. Now, what do we mean by rate of forward reaction being equal to rate of backward reaction? It simply means that rate of forward reaction is said to be equal to rate of backward reaction when the concentration of products and reactants no longer changes with time. So we can say that rate of forward reaction is always equal to rate of backward reaction when the concentration of products and reactants no longer changes with time. Yes, when you realize that concentration of products and reactants no longer changes with time, you can say that rate of forward reaction is equal to rate of backward reaction, and from there you say that the chemical reaction has reached equilibrium. Now, there are other conditions that will make a chemical reaction to reach equilibrium. One, when the free Gibbs energy is equal to 0 and when the equilibrium constant is equal to 1, we can say that the chemical reaction has reached equilibrium. What do we mean by that? Okay, we noted in chemistry that change in G is equal to change in H minus T change in S, where change in G is called free Gibbs energy. Change in H is called enthalpy change. That is what? The heat of reaction. Whereas this is temperature in Kelvin, and this is change in S, entropy change. That is, we're talking about the degree of the disorderliness of the reaction. Are you getting it? Now, when this is said to be equal to 0, when this change in G is equal to 0, we can say that change in H is equal to T change in X. That means for a reaction to be equal, outside that change in G must be equal to 0, okay, equal to unity or 1. We can also say that a reaction is said to be what? To be in equilibrium when change in H is equal to the product of the temperature in Kelvin and what? Entropy change. Now, how did we come about K being equal to 1? We also noted that this free energy is equal to negative of RT ln K, where R is universal gas constant T is the temperature, ln K. And so when this is equal to 0, we could say that ln K is equal to 0. And what do we mean by ln K? Ln K means 2.303 log K equals to 0. Therefore, log K is equals to 0. And log K means log to base 10. Log to base 10 K equal to 0. Now, 10 raised to the power of 0 will be giving you that K equals to 10 raised to the power of 0 equals to 1. That is how we got that the equilibrium constant K should be equals to what? 1. Change in G equals to 0. Therefore, enthalpy change should be equal to product of the temperature and entropy change. That means this condition, when you see them, and these ones we wrote before now, when you see them, it simply means that that chemical reaction has reached equilibrium. Now, it's important for us to note what we call law of mass action. In this chemical equilibrium, there is what we call law of mass action. What does this law of mass action states? It says that when you have this reaction, let's have this reaction. When you are given this reaction, and they said it has what? Reaches equilibrium. This is called the first constant, and this is called the what? Second equilibrium constant. Now, this K1 is talking about the one of forward reaction. This K1 is talking about what happened when this goes to what? Formation of products, as you can see. Now, this obeys the principle of Le Chatelier's principle, which says that get the concentration of the products raised to the power of number of mole. When you see this symbol like this, it means concentration in chemistry. When you put it like this, it is not concentration. When you see square bracket like this, it means concentration. So this square bracket is what we will put here, raised to the power of number of mole of that product C times the one of what? Raised to the power of product of what? Then divided by, you come for the reactant own, raised to the power of A, then times raised to the power of B. That is about your K1. Then, when you are talking about the opposite, that is the backward reaction. So this one will be favoring the forward reaction now. But when you are talking about K2, K2 means we are now taking this to be the reactant and we are now taking this to be the product. As you can see, this will now react to give about this because they have attained to equilibrium, dynamic equilibrium. And so what we'll be saying is now, for K2, we say A times what? B all over what? C times what? D. So from here, we could conclude, or we can conclude that K1 is equal to, if you check what is happening here, you will notice that this one is opposite of this one by reciprocal. Opposite. You understand? So we will say K1 equal to 1 over K2, or K1 times K2 equals to 1. That means the product of equilibrium constants of the forward reaction and the backward reaction is always equal to 1. Are you getting it? Now, we want to give some example of how you can represent your equilibrium constant when you come to chemical equilibrium. We have an example. When you have these reactions, When you have these reactions, this is in gas, this is in gas, to produce what? 2 in gas. Your equilibrium constant K is concentration of the what? Product raised to power of the number of what? Mole, which is 2, all over concentration of the what? Reactant raised to power of 1 times what? Concentration of the reactant raised to power of 3. So this one raised to power of 2, this one raised to power of 1 because the mole is 1, this one raised to power of 3. Now, because they are gaseous, we will have this to be the what? Equilibrium constant. Yes, it means that this will be the equilibrium constant of this reaction. But it's possible for one to have a reaction like in solid state, calcium carbonate in solid state, undergoing or attaining to equilibrium. This is scale 1, this is scale 2, or we take only one scale to give you calcium oxide plus carbon 4 oxide in gas. In this case, our equilibrium constant K will be equals to this one raised to the power of 1, because number of mole is 1, number of mole of this one is 1, times what? This one raised to power of what? 1, because number of mole of it is 1, then all over this one, this calcium carbonate raised to power of 1. Now, if you look at this, you will notice that what matters to us is the one that are in gaseous. It's the gaseous one that matters to us. Yes. Now, this one have solid and gaseous. We will cancel the one of solids. They will clear. So the final equilibrium constant of this becomes only what? Carbon 4 oxide. So this becomes the equilibrium constant of this reaction, because it is only this that is in what? In gaseous form. But for this one, we say ammonia raised to power of 2, nitrogen gas raised to power of 1, and hydrogen gas raised to power of 3. That is how to represent this. Of solids are said to be constant. They are said to be constant, and so we cancel them. We'll cancel it out. They are constant. We only keep the one of gas. That is why, because these ones exist in gaseous form, we left them what? This way. Now, it's also important for we to tell you, I made mention of change in G equals to minus T change in S. Now, what do we mean by change in G? We say it is called free gives energy. Energy for doing work. Are you getting it? Energy responsible for one to do work. This is enthalpy change, which we call heat of reaction. Heat of reaction, where we have endothermic and exothermic. Endothermic when there is gain in heat. Exothermic when there is loss of what? Heat, energy. Then this is temperature in terms of what? Kelvin. That means if it is given in Celsius or centigrade, you convert it to Kelvin. Now this is entropy change, disorderliness of a reaction. Once a reaction disorderliness is high, we say that change in S is high. Once a reaction occurs easily, we say that this is high. Are you getting it? Look at what we mean. We said that a reaction is said to be spontaneous if this. Okay, let's start from the beginning. A reaction is said to be at equilibrium if this is equal to 0, okay, equal to 1. Are you getting it? And also change in H equals to T change in X. We say that a reaction is said to be at equilibrium. Now, what if a reaction is not an equilibrium? Once a reaction is not at equilibrium, it means that either it is spontaneous or it is not spontaneous. How? When change in G is equals to negative and change in X is greater than 0, we said that this reaction is very spontaneous. What do we mean? Take for instance, this is marker. Is it possible for this object called marker to fall from up to down? If I release it from this height, what do you notice? It will fall. Then we will say that it is spontaneous for this marker to fall from high to low. For this marker to fall from high to low, it will be very spontaneous. It will occur naturally. That is what we mean by being spontaneous. It will occur easily, it will occur naturally. For something to move from high to low part of anywhere. Are you getting it? But what if I keep this marker down? If I keep it down and I want it to go up, if I remove my hand from this marker now, do you think it will go up? No. It can only go up when I apply energy to it. And you know what energy means? Force times distance. When a force moves an object towards a certain distance, we'll say a work is done. We noted that work is equal to force times distance. This is elementary physics. Are you getting it? That means a movement is said to be done when a force move an object towards a certain distance. So for this marker to move up, work must be done. That means I must apply energy to it for it to move up. That is when you will now say that change in G is positive or is greater than 0. That means energy required to do work is applied. Energy required to do work is 100% applied. That is why this marker can move from down to up. Are you getting it? No matter how this energy was applied, whether you use charm to do it, it's still force that you apply. It's still energy that takes place. If it's juju you are used to do it, it's still energy that do take place. If it is you raising it with your hand to up, it's still energy that you use to raise it up. Are you getting it? So once a body is pushed up, it means you applied energy, you applied force to push it what? Up towards this distance. So energy is applied. In that case, energy at work, which is this free energy, is no longer negative but positive. That means this makes this reaction to be spontaneous. Once change in G is greater than 0, automatically what will happen to change in X? It will no longer be greater than 0. Change in X will be what? Less than 0. Once change in G is greater than 0, change in S will be less than 0 because the rate of disorderliness will not be high. Look, just watch it now. This marker now, if it's to go up, I am the one controlling it by the energy applied to push it up. That means I apply energy. So energy is involved. Are you getting it? And this marker will not move up anyhow because I am controlling it with my energy. But this one now, the spontaneous aspect, this is for spontaneous or natural process. Spontaneous or natural process. Are you getting it? Why this is for non-spontaneous? Are you getting it? So for this one now, it means if I just remove my hand from this marker will just fall anyhow. the degree of disorderliness of it will be high. It will just fall anyhow. If this is a harmful object, it can wound someone because it just fall anyhow. Are you getting it? But when it's down, for him to move up, I will be the one to apply energy by applying force to push it towards a certain distance. I believe you understand this concept. I noticed that when I was talking about, I didn't explain it in details. So this is about when it will be non-spontaneous, or when we will say that it is no longer a natural process. A natural process means a process that occurs on its own without the help of anything. It just occurs on its own. That is natural process. It means that in that case, I didn't apply any energy. The energy is negative. Energy is not applied. It just what? Fall on its own. Whereas the entropy will be very high. So if you are seeing this in your JAMB, in your WAEC, in university, be able to understand the concept very well. For a chemical reaction to reach equilibrium, change in G will be equal to 0, K will be equal to 1, change in H will be equal to this. Then for it not to be equilibrium, for him to be spontaneous, it means that this is this and this is this. For it to be non-spontaneous, it means that this opposite will be the order of the day. I believe you understand it very well. So if there is anyone you do not understand, you can use my DM or use my WhatsApp number or use the comment box on YouTube and ask your question. Okay? Now, we also said that when you have this reactant giving you this product, when you have this reactant giving you this product, okay, let's put it in reversible because we are talking about equilibrium. And this is your K1 and this is your K2. We said your K1 will be equal to this one raised all over what? This one, right? Therefore, K2, when you talk about K2, it means that this one will not be the reactant to produce this. This is the arrow for K2. K2 will be, this is the reactant, this is the product. So this is the reactant for K2 and this is product. Then for K1, the forward reaction, this is the reactant and this is the product. That means the K1 is talking about equilibrium constant for forward reaction, while K2 is talking about equilibrium constant for backward reaction. So from here, we can see reciprocal. We say K1 equal to 1 over K2 and K1, K2 equal to 1. We talk about this. Then we now say again, when you have this to be your reaction and this is your K1, then when it's like this and we have number of mole, a number of mole added to this, and you are asked to get the value of this K. When this is A and B, this K1, you tell them that K will be equal to K1 all raised to power of what? N. The number of moles added. That means if you are given, let's say now A to produce B and this K1, and here is 3A to produce 3B, automatically the implication that here will be equals to what? What is your K1? You say your K1 all raised to power of what? 3. That is just what you have to do. So if your K1, equilibrium constant of K1 is, let's say now 10, it means 10 raised to power of 3. If equilibrium constant K1 is maybe 5, whatever, you say 5 raised to power of 3. It gives you your answer because of what we have here. Are you getting it? Now, when you have this, another scenario, and you are having what? C to give you what? D. It then means that if you are adding them, this is your K1 and this is your K2. Are you getting it? The implication is that when this is given to you, that is the summation of this reactant and the product, The implication is that this K3, which is for this one, will be equal to K3 is equal to product of what? K1 and what? K2. So if here is 2 and here is 3, K3 will now be equal to 2 times 3, 6. Are you getting it? So you just multiply these two equilibrium constants, you will get it. Okay? Now, we want to look into another aspect of different ways this equilibrium constant can be represented. Equilibrium constants can be expressed in different ways. You can express them in terms of concentration, in terms of partial pressure, and in terms of whole fraction. So we can express equilibrium constant in terms of concentration, partial pressure, and whole fraction. What do we mean by that? For partial pressure, we say Kp. Let's say Kp, equilibrium constant of the partial pressure. We say it is equals to RT Kc RT raised to power of change in N, where is equilibrium of the concentration. See how they are related now. You can also represent it as this equals to Kx you can see now. Yes. So we can represent them in this way. That means, what do we mean by change in N? What do we mean by Kc? Equilibrium constant with respect to concentration, equilibrium constant with respect to whole, equilibrium constant with respect to partial pressure. That is how they are related. That means this you are seeing is equal to this. Then what do we mean by PT? This is total partial pressure. R is the universal gas constant. T is the temperature, so to speak. And change in N mean number of moles of the product minus number of moles of the reactant. Do you understand it? That means change in N any P minus any R. Number of moles minus number of moles of the reactant. Do you get it? Now, that means when change in N is equal to 0, when change in N is equal to 0, you put 0 here, everything here will be 1. RT raised to power 0 is 1, because in indices, anything raised to power 0 is 1. 1 times this, that will be giving you that Kp equal to Kc. Then this one, anything raised to power 0 is 1. Pt raised to power 0 is 1. This will also give you that Kp equal to Kx. So they can ask you, when can we say that, or when the change in number of moles of a reaction is equal to 0, what happens? You try to tell them that equilibrium constant of the partial pressure must be equal to equilibrium constant in respect to their constant. Then equilibrium constant in partial must be equal to equilibrium in respect to what? Whole fraction. Are you getting it? That is what mean, or what it means when changing to 0. So please note this condition. It occurs when change in N is equals to 0. What do we mean by change in N? Take for instance, when you have this reaction to give you if this is a reaction, if this is a reaction given to you, this is the number of products, while this is the number of what? Reactant. So change in N will be equals to what? 2 minus 1 equals to what? 1. That means for change in N to be equal to 0, here should be 1, here should be 1. Then we now say that Kp, equilibrium constant with respect to partial pressure, must be equal to Ks with respect to what? Whole fraction. or Kp must be equal to what? Kc. That own equal to the concentration own. Are you getting it? So that is how to get your change in N equal to 2 minus change in N. That is Np minus Ner. 2 minus 1 equal to 1. Are you getting it? So I want you to understand this concept well, because we will be solving a lot of questions now. We'll be solving a lot of questions, and I would like you to use this information you have gathered to be able to understand these questions we'll be solving. Let's see how to solve these important problems on chemical equilibrium. Yes, they are very important. Question number 1. Calculate the equilibrium constant at 30 degrees Celsius if change in G is, which we call free Gibbs energy, is minus 11 kilojoules per mole. Now, look at how to solve it. You have to tell them that I know this formula that says change in G is equal to minus RT ln K. And we are looking for K, that is called the equilibrium constant. First of all, convert your temperature to Kelvin, because the SI unit of temperature is degree Kelvin. Oh yeah, how do you do it? Add 273 to 30. 273 plus 30. That will be giving us 303. Are you getting it? Then our R is constant 8.314, right? Yes, please, this R is constant. I'm not the one that discovered it, okay? It's constant. Then this change in G is given to be this. Change in G is equals to minus 11 kilojoules. That means it is equal to minus 11,000 joule per mole. That is about change in G, so to speak. Now, we are to make ln K subject of what? Formula. How can we make ln K subject of formula? We say ln K is equals to, come here, change in G all over minus RT. Now, if you are removing ln from one side of the equation, opposite of ln is exponential. That E you know. We say I'm removing ln. I'll be having what? Exponential. Because I remove ln from the other side of the equation. Are you getting it? I will be putting exponential at the other side. Exponential raised to the power of change in G all over minus RT. Now, in mathematics, exponential is equivalent to 2.718. Okay, equals to 2.718. Raised to power of, anytime you see 2.718, it means exponential. It simply means what? Exponential. Okay? Now, what is our change in G? We'll have it to be minus 11,000. Minus 11,000 is our change in G. Then what is our R? We say all over minus R is 8.314 times, what is our temperature? 303. So we have to simplify this. So it's better you use your functional calculator to sort it out. Okay, this is my own. Open bracket 2.718 raised to power of bracket 11,000. I will close the first bracket. Okay, minus 11,000. I will close the first bracket. Then I will now say divided by bracket. The second is minus 8.314 times 303. I will now close it. I will press equals to. So if you use your calculator to simplify your own, you will be having K equals to 78.74. That is your answer. Please use your calculator to confirm this we solved and tell me in the comment box if we are correct. Thank you. To answer question number 2, for a reaction to occur spontaneously, delta H of the reaction must be dash. The answer is negative. It must be negative. Why did I answer negative? In the introduction of this topic, I said it that for a reaction to be spontaneous, that change in G must be less than zero. I explained it. I also said that change in S should be greater than zero. Change in S is degree of disorderliness. Entropy change, that is the degree of disorderliness. It must be having high degree of disorderliness, and you will require little or no energy applied. That is what we mean by this. Then we also said that for this one, the care should be greater than 1. The care should be greater than 1, and change in H should be equal to negative. That is less than 0. Change in H should be less than 0, care greater than 1. We call this the equilibrium constant, and call this entropy change greater than 0 and this. That means we explain and we said if you want to throw something from up to down, now if I release it, I don't need to start pushing it down like this. No, I'll just release it. It will occur naturally. It will fall down. Bah. That means every spontaneous reaction is called a natural process. It's something that occurs naturally. Are you getting it? So it will fall without the help of any energy being applied. That is meant by this less than 0. And as it's falling, it will fall anyhow. If this is a harmful object, it will fall and destroy a lot of things because it will not have a control. But when we say that something is non-spontaneous, non-spontaneous is opposite of spontaneous. It means that this one should be greater than 0. You must apply energy. That is what we mean by this. You must apply energy. That means if I have something like matter like this and I want to push it up, I need energy to be applied to push it up. True or false? Yes. Even if it's coming from witchcraft, anyone, juju, it is a force that you are applying. Are you getting it? And when you apply the force and it causes a body to move towards or cover a certain distance, if you apply a force on an object and it moves that object to cover a certain distance, a work is done. Energy has been done or has been applied. That means force times distance. We talked about it before now. Yes, it means I apply energy to push this up. So you see me pushing it up now, it's because I chop better eba now. You understand? So I have energy to push it up. Okay. Now, in this case, we also say that entropy change will be very low. That means the degree of disorderliness of it will be very low. You see me, I'm controlling it now. It can't fall anyhow. You see me, I'm pushing it up. It can't fall anyhow. So the entropy change is low. Are you getting it? And we also say that this should be less than 1. The equilibrium constant should be less than 1, and the enthalpy change, the heat of the reaction, should be what? Greater than what? 0. So this is for non-spontaneity of a reaction. Why this one is for the spontaneous aspect. Are you getting it? Please don't mix it up. It's self-explained. Okay? We go to question number 3. In question number 3, we are given this reaction and we are asked to get the K of the constant, the equilibrium constant of the concentration. Are you getting it? The equilibrium constant of the concentration, given that equilibrium constant of partial pressure is this, this, and this. 1/8 here. This is the pressure, the total pressure given. This is the temperature in Kelvin. And this is the equilibrium constant of the partial pressure. Are you getting it? Now, if you are given this type of question, it is simple. You tell them that I remember that Kp is equal to Kc RT raised to power of change in N. Are you getting it? We have this formula. Now, what is your Kp? Kp was given to be 0.157. What is your R? We say it's 8.314. It's constant. It's always constant. T is equal to 300 degree Kelvin. That is our T. and we are looking for, okay, change in n. Wow, I've talked about this. This is in gas, this is in gas. The change in n is equal to 2 minus 1. The mole of this is 1. That number of mole of the product and number of mole of the what? Reactant. Get the total number of mole of the product minus the one of the reactant. Are you getting it? And so we'll be having it to be 2 minus 1 equal to 1. So you put it here. That means my Kc, making it subject to formula, what is my Kp? 0.157 all over RT raised to power this 8.314 times 300 all raised to power of 1, because their power is 1. Okay, I will go by my calculator again. Divided by bracket 8.314 times 300. I am getting 6.3 times 10 raised to power of minus 5. Please use your own calculator and compute your own. Let's see what you get in the comment box. Okay? Now to solve question number 4. Calculate the Kc for the reaction of this if the Kc of this is this at 500 degree Kelvin. This is when you apply those principles we talk about in the introduction part of this video. What do we mean? They gave us the Kc of this. That means the Kc of this is this. How is this related with this equation? How is this equation that they gave us the Kc, how is it related with the first one? Do you notice that when you carry 2 to multiply this, you have 2. When you carry 2 to multiply this, you have 2. When you carry this to multiply this, you have O2. That means our first equation, the Kc of the first equation can be gotten by multiplying. That means, look at this one, we are looking for this. Okay, our Kc for the first equation can be gotten by dividing everything here by 2. If you divide this by 2, you have this. Divide this by 2, you have this. Divide it by 2, you have this. That means my new Kc what? 2 will be equals to my Kc 1 or raised to the power of half. Because the number I will get here to get this is by dividing this by what? 2. So 1 over 2 times this will give you what? This. 1 over 2 times this will give me this. 1 over 2 times this will give me this. That is what we mean by when I say A, and we have this to be K1. Then we have any A, any B. I get it. Means when you use any to multiply this, and you use that any to multiply this, the implication is that the K for this one, K will be equal to K1 raised to the power of that n. That n you use to multiply. So the n we use to multiply here is half. Half times this, half times this, half times this. So that is why we are raising to the power of half. So what do we have here? Our Kc1 is 9.71 times 10 raised to the power minus 13. So we will be getting the square root of it, because 1 over 2 as a power. When you have 1 over 2 as a power, it simply means take the square root. Are you getting it? Okay, so that is what we mean. Well, that is what we mean. I've explained this, that this will be raised to the power of n, the n you have. So we have gotten the raised to the power of n, which is half. Half is what we use to multiply. Our n is replaced with half now. So that half as a power simply means square root. Now, square root of this, let me use my calculator also. I will now say 9.71 times 10 raised to the power of minus 13. That will be giving me that the answer is Kc2 equals to 9.9 times 10 raised to the power of minus 7. 9.9 times 10 raised to the power of minus 7. That is by approximation. That is for this. Go to question number 5. Now to solve question number 5, calculate the Kc for the reaction this if the Kc of this is this. If you notice from these two reactions, you notice that this one move forward like this, while this second reaction is this moving backward. This move like this. For the second reaction, this one is moving like this. Look at it now. This plus this gave me this. Now for the second one, this is giving me this and this. That means we have come back to the formula we wrote before. A give me what? B. This is scale 1 and this is scale 2, where we said that scale 1 equals to 1 over scale 2, because this scale 1 is for this and this is for this. So that means they gave us the one of scale 2, the reverse own, for this to go back. They gave us scale 2 and they're asking us to get the scale 1, the one of forward. Now to get the scale 1 from this formula, I will say therefore my Kc1 will be equals to 1 over this what? Second Kc, that is Kc2. 1 over 8. And what is it? 9.71 times 10 raised to power minus 13. Once I compute this, I have done with this. That is why if you understand these principles very well, you will not be wasting your time to solve a question. Let's see. 1 divided by bracket, please package this well. 1 divided by bracket 9.71 times 10 raised to power of what? Minus 13. So that will be giving us Kc1 equals to what? 1.03 times 10 raised to power of 12. That becomes the answer. Yes.